Hey there. So, change of plans. I was originally going to have Bryson do this lecture, but he's unable to do it on Monday. So, I'm recording a lecture for you. It's Saturday night, 8 o'clock. The game's about to start. So, I'm going to make this quick. Hopefully, watch this Monday. But yeah, so let's get started. We're going to talk about TLS. You should be somewhat familiar with TLS, right? Because we've talked a lot about our simple TLS, and it's got some changes to it, but it's got the feel of TLS. So this should all be kind of familiar. So I think this will be relatively quick, and especially if you're watching this at double speed, then it'll be even quicker. Okay, so TLS, Transport Layer Security. This is a really popular protocol. It's kind of the go-to protocol for any application layer protocol that wants security. So we see that with HTTP, got HTTPS, port 443, secured. We have MQTT. There's MQTTS, which uses TLS to add security as well. There's other protocols, co-op, that uses TLS. So it just kind of any application layer that needs security, TLS is often the one we go to because it provides so many great guarantees. And unlike UDP versus TCP, where it's like, oh, do you want reliability or do you not? Can you get away with it? Like if you want security, then you want all of security, right? You don't typically ever like say, oh, I don't care about this or but I do want this one. Once again, it depends. Sometimes you do, but generally speaking, you want your data to have confidentiality, integrity, and authentication. And just to make it really clear, you should know what these words mean. If you don't, go and look that up from previous lectures and that. Like you should feel confident what confidentiality means, what integrity means, and how to achieve that, I guess, authentication. But these are all things we've talked about, so you should be familiar with them. Kind of a little history behind this. It originally started with SSL, and that's kind of was predominant protocol, a while ago, but then it got deprecated in 2015. You still see SSL around. Often they mean TLS, but I guess they could mean SSL if it's really old. I think I'll just say TLS. I think I got in pretty good, but I learned SSL, so that's kind of sometimes I might accidentally say SSL instead of TLS, but I really mean TLS. Okay, so we've already kind of seen the pieces here. We have this handshake phase where Alice and Bob, exchange some information. Then they derive these keys. Then they start transferring the data. And then, of course, then they close a connection. Simple TLS, we have a little shorter of a handshake in that we don't really specify what schemes we want to use. We just assume it's only one scheme. It's all been defined. But we still do our key derivation. So that should be about the same. Our data transfer is only going one direction. So in true TLS, it could be bidirectional. And we have the keys in our simple TLS story do that. We just don't use them. And we totally skipped on connection and closure. And I'll talk about why that's important in a true real TLS scenario. But I just felt like it was too much for simple TLS. And so I didn't include that component to it in simple TLS. So this is what it looks like, just to kind of be clear, be really clear. I know it's called transport layer security, and it is providing transport layer security, but it lives at the application layer. So that's something you should be familiar with, that it lives and implemented in the application layer, but it is providing security to the layers below it. But you might be confused and thinking, oh, it's transport layer security, so it must be in the transport layer. That's not true. Only TCP and UDP are in the transport layer. TLS is at the layer above. So here in this first column, we have HTTP version 1, didn't have TLS, so just use TCP and then IP. Version 2, we add the option for TLS, still using TCP IP. And then finally with HTTP 3, essentially just got HTTP 2, but now it has this new component, Quick, that is now using UDP and IP. And what they've done is they've essentially, because TLS and TCP were two separate protocols and two separate layers, there was no kind of synergy there. TCP had to do its thing, and then TLS had to do its thing on top of that. And that added for a lot of round trip times. But by saying, well, let's get rid of TCP and put it, put all the reliability up here, now you have this synergy, which we call quick, where we can combine all the things that TCP was doing with its handshake with integrate with TLS. So we're able to get that benefit there. So now that's what HTTP version 3 is. So here we see, if we go back to, the version 2 of HTTP, we have this TCP ACK and SYN-ACK, the three-way handshake. Remember, though it is three-way, it only takes, it's one round trip, and then on the third part of it, we can be sending data as well. So we can be acknowledging while also sending data. So while we acknowledge, we are sending our TLS hello message. Then the back and forth with getting the certificate, and then we encrypt the master secret. So this all should be pretty familiar to you from what we've done what we did with doing with simple TLS. Here we have the client request, and simple TLS we don't have a client request. It's just got the server sends us data, but you could easily see how it could handle a client request and a server response. So the big issue with this is it's a lot of back and forth. 3 round trip times just to be sending data. That's far too long. We don't like that. We don't like waiting around for our data, right? So you'll see that a lot of innovations, quick, but there's also zero RTT with TLS, all these things to say, how can we fix this problem? And I'll show you an article at the end of this that kind of highlights that a little bit more, why that's a big problem. Okay, in terms of the keys, I've said this before, but it's worth repeating that it's considered bad practice to use the same key for more than one cryptographic function. So we wouldn't want to use the same key. We could use the same key, but it's not a good idea for encryption and integrity protection, for authentication. Sorry, for integrity protection, not authentication. So that's why we drive 4 keys. We could just get away with 2 keys, one for the server, one for the client, but then they'd be serving 2 purposes, and that's considered a bad idea. And so we generate 4 keys. 2 of them are my keys if I'm the client, 2 of them are the server's keys. So we use 1 key for the message authentication code, another key for the encryption for each end of the nodes. So we have these 4 keys. We drive these keys, so we only have 1 master secret, but we drive these keys using something called a KDF, a key derivation function. I don't know, some magic, not really magic, some fancy function that can take some secret and expand that secret into more, and do that in a reliable way that doesn't leak any information about the original secret. So we take this master secret and potentially some other random data and create these new keys. Because the master secret isn't big enough to generate all 4 of these keys. We have to take that master secret and then expand it out into a bigger secret that then we break up into 4 keys. So that's what we're doing with TLS. Now, this is an interesting problem. We see this with simple TLS. We have to kind of have this header when we're saying that we have to break up the data that we're sending into different chunks. That's because TCP has this byte stream abstraction, right? It's just a stream of data. You might get some of the data, you might get all of it, you don't know. But that doesn't work very well with encrypted data, right? Because where would you put the MAC? Where do you put this message authentication code? If you put it at the end, let's say it's a TCP connection, but you have this MAC at the end. What if you say, okay, it's at the end, and then you close connection? But what if it got messed up? Then you have no way to request it, or you have to wait a long time before you can actually validate the data and make sure it's correct. So what we do instead, what TLS does, is it breaks the stream up into what they call records, different packets, essentially chunks of data of determined size. And then on that record, you put a MAC and you encrypt that MAC. And so now a receiver just has to work at these different record levels. I don't know why they're called records, just I guess every layer, every protocol has to have their own terms. And we're using symmetric key at this point. We had used public-private key just to initiate, but once we have this master secret and then we drive our keys, Now we have the symmetric key. So like in this case, the key for the client. So the key for the client is used to encrypt this packet, this record that has a length and data and a MAC, message authentication code. This is actually not quite right. We have one more piece that we're missing. So let's work our way up to that. What's a possible attack on this data stream? Like what could someone do about this? That's worth thinking about. So one issue is that they could reorder the packets. Now, this is an interesting problem because I think Isaac pointed out that you couldn't like really reorder the packets because TCP would take care of that. But you could take the TCP data and say that's not encrypted. That's still normal TCP data because remember, it's just the payload that TLS is encrypting. And you could manipulate the sequence numbers and make TCP think it's out of order and so put it into different order than what actually was originally intended. That would be a hard thing to do. If you're man of middle, then you could do that. But if you're not a man of middle, then it might be a little harder, to get that done. So what we use with TLS is we use sequence numbers. So it's not just enough to have data and the length and the MAC. We also need to have sequence numbers, our own sequence numbers at the TLS level to make sure that TCP hasn't done anything wrong. Not that TCP would ever do anything wrong on purpose, but that someone hasn't manipulated the TCP data to cause problems for us. So we now have to have sequence numbers. That's an extra thing we need to have. Another issue we have is this idea of this replay tag. Of could we replay the data? And so we've talked about that over and over again. So we use nonces for that. Okay, the last thing we need. So we've added to this. We need a sequence number, which simple TLS uses. There's one more attack that simple TLS does not protect against, but real TLS does, is what's called a truncation attack. I think it's really genius. All these things that people come up with, I think it's really cool. I'm not that clever, I guess. What if you could forge a TCP closed connection? What if I could trick you? You're receiving data from the server, and I quickly inject in there a TCP closed connection. That's not that hard to do. I just have to kind of guess your sequence number, I could, or your ACK number, and I could just send this closed connection. And so what could happen is you would receive this close. You have no really way of verifying that the server wasn't the one that sent it. And so you'd say, oh, I guess they're done sending me data, and you'd close it. But there actually might be more data for you to receive. You just didn't know that because you thought the TCP connection was closed. So that's not a great thing. We don't want, we don't want to, even if it was encrypted, this could still be a weakness. Even if you're using TLS or, but TLS protects against this. And how it protects against it is it adds a type field to its payload. So now there's two types of records, two types of data. There's 0 for data and a type 1 for close. So I'll look for that. And if I see the close, then I know that the TCP connection close should be happening soon. If I'm just getting type 0 and then all of a sudden you see the connection close, I know something went wrong, that the server wasn't the one that sent it, or something went wrong if it was the one that sent it, but something happened and I should disregard that data, essentially. So now we compute the MAC on the length and the type and the data, of course, because we don't want, you might be, tempted to say, let's just compute the MAC on the data. But then that means someone could change the type or someone could change the length. Of course, it is encrypted. We encrypting with this key of the client, but you can, it's hard, but you could maybe get lucky and flip a bit, and that could be the bit that corresponds to your type field. So you still, even if it's encrypted, you still want to provide the MAC on top of for both the data, the type, and the length. Okay. So simple TLS is implementing TLS 1.2, but there is TLS 1.3. It's not that new, but it's, these things take time to roll out. And so it's tried to simplify things quite a bit from TLS 1.2 to 1.3. So one of the things it does to simplify it is it limits the cipher suite choices. So I mentioned this, I don't know if I made it very clear, but there's a negotiation that happens between the client and the server. Say, hey, what like ciphers like are what key sizes can you use? And TLS 1.2 had 37 different choices. And that's to accommodate lots of device types because maybe, oh, we haven't done a software update for a while, so you support the old version, or maybe your computer isn't very capable, so it has to do the old version of something, so not as secure. Remember, that led to a downgrade attack, we called it, where if I could insert somewhere and kind of remove some of the higher end choices, then I could artificially weaken your security, and then I could try to brute force that or do something to manipulate the data. So TLS 1.3 said we're going to be done with all these choices. We're only going to give 5 choices, and then those 5 choices are pretty solid choices, very secure, and so then there's a lot less risk of the problem of downgrading someone's connection. It also uses Diffie-Hellman for its key exchange rather than RSA. So that's a big change. When you know about Diffie-Hellman, you know about RSA, so you should understand what those mean. And then the last thing it did is, we have this, if we go back to this diagram right here, we have this MAC, and we also have this key that we've encrypted the data with. So we have to first decrypt the data. Once we decrypt the data, then we have to calculate the MAC on this data and type in length. Kind of these 2 separate steps. That could be kind of slow. So TLS 1.3, so let's combine these together. Let's create this authenticated encrypted data. So then we can do this all together. So that's a kind of a cool thing that does. And then increase the key size as well, or in the encryption hash. So let's go through this a little bit. Nothing crazy. It adds a lot less round trips now, but it's kind of at the heart of it's all the same. And in terms of it has indicates a cipher suite. They agree on who chooses what. The server gets a self-signed certificate. Not sorry, uses its certificate. They generate keys. So at the end of the day, it's all kind of the same thing. This back and forth to drive these keys and then send this request. A little bit faster than TLS 1.2, but you can imagine you could optimize TLS 1.2 to make it faster, and that's exactly what TLS 1.3 did. One thing I want to talk about though is TLS 1.3. It has a mode called 0 RTT, 0 round trip. And this is kind of an interesting mode. It's if you've already talked to the server in a recent amount of time, what TLS 1.3 lets you do is pick up where you left off and say, hey, I'm going to resume this connection using the same security kind of primitives or principles I have, maybe the same master secret I did before, and I can just send my client hello and some parameters already and the already encrypted application data. So I'm essentially leveraging an old, communication scheme I had before. It can't be super old, but maybe you talk to the server often, then this is a way to speed up even more because now it's 0 round trips to have it be encrypted. Obviously, there's still 1 round trip to get the data, but there was no setup, so the setup is 0 round trips. So it's kind of interesting idea. But of course, what's the saying? There's no free lunch. That comes at a cost. It's not like we're adding round trips just for the heck of it. It's because that's the most secure. But what we found is people often care more about speed than they do about security. And so what we can do is we can make a trade-off. We can say, hey, we'll give you the 0 RTT, but you can only do certain things with it. Because what it's vulnerable to is replay attacks. What if I'm listening into this connection and I see this client hello with application data and I say, okay, great, I'll play that back in an hour. And so I send that back. I might not be able to read the data, but that could cause problems because what if that HTTP GET request did something like, I don't know, I always use the example, paid someone a paycheck. Hey, pay Bill, their, $1,000. Then if I take that and I play it back, then Bill would get paid another $1,000. Okay, awesome. And keep on doing that. So that's not a great, thing. We don't love replay attacks. But what we can do is we can say, hey, let's design our systems such that it only works for GET requests. And as long as it doesn't change the state of the server. So going back to my example of paying someone a paycheck, that would not be valid. You could do a replay attack, but the server shouldn't allow zero RTT TLS to be done if it's changing the state of its server somehow. So if it's like, hey, get me this web page, then that's fine. I'll get you the web page as many times as I want. It didn't change any state about what the server's doing. And, you know, as an attacker who did this replay attack, I can't receive that data, or I can't, decrypt the data. So it doesn't do me any good. It only does me good if I can change the state of the server somehow by sending that request. But we've limited it, said, no, we're not allowed to be able to change the state of the server if we send this RTT, if we're using RTT0. Then we've essentially taken that strength away. I don't love it in that that relies on people designing the servers to honor this, and people aren't really good at following instructions, or always doing the best things. So I feel like that's still a little scary to me that we're doing this, but I get it. Speed matters. We care about that. Okay, so that's it for TLS. Like I said, this is kind of short. I guess I did want to show real quickly. Let's see here. Yeah, this article right here. So I did post this article to Learning Suite. I just barely added it because I thought it was pretty good. One thing I wanted to show, yeah, I mean, it really highlights the cost of latency. I know, round trip times, who cares about round trip times? But it does matter. Maybe it doesn't matter as much for the United States because we tend to have pretty good pings, pretty good latency, but there's lots of other countries that don't have that. And so that could be prohibitive to have something that takes so long. And then the other thing I thought of, that I thought was kind of cool is, depending on what kind of connection you're on. If you're on Wi-Fi, and then it's like, okay, great, this is not a problem. But if you're on 3G or 2G, these older, maybe satellite, maybe you have a Starlink connection, that round trip time is a lot higher. There's a lot more latency. So doing those round trip times every time is really adds up. And so this might not be something that you care about. You're like, oh, my internet's plenty fast, even with multiple round trip times. But as we try to, push the internet more to more places and allow more people to access this really important asset, making it fast and usable, but still secure for them is a really important endeavor. So this is a really interesting article to read that kind of goes through some of these numbers and talks about it. Cloudflare has really good articles because they're in the middle of this. They're providing a lot of these internet services that we're talking about, like CDNs and DNS and all this stuff, and so they have some really good data and really good experience with this stuff. Here's this attack that we talked about where the client sends a request, a post request. Maybe I could listen to that post request and then play it back later. Change the state of the database, insert something in here. But as I said, but also as they say, you're only, this figure is wrong in that we did a post request. You're only allowed to do GET requests with no query parameters. If you don't know what that means, that's totally fine. Just you're only allowed to do GET requests that are kind of plain GET requests. So if you're interested in this, check out this article. It's really good. I think it's like a pretty quick read. But yeah, that's it. Hopefully this all makes sense with TLS. Hopefully you're working on your labs, simple TLS. It's not too bad, but you should be working on it a little bit here and there. I will see you all in a little bit. Have a good day.